Okay, let's continue on with this worksheet. We're on question 7. Slide that up to the top. A ping pong ball has a charge and is suspended in a parallel plate apparatus. Oh, cool. So we got parallel plate, ping pong ball sitting in the middle here. The ping pong ball is negative and it's being suspended. This is 12 centimeters apart. This is question 7. So gravity's pulling down on the ball and electrostatic force is pushing up. So they're going to balance each other. The bottom plate here, is asking here, the bottom plate has to be negative. Negative and negative repel will push the ball up and gravity's pulling down. And they want to know the voltage between them. So we know that force of gravity will equal the force of electrostatics. Gravity will just be mg. The force of electrostatics would be the charge times the field strength. Okay, it's a parallel plate system, so field strength equals voltage divided by the distance of separation. So we got lots of numbers here. We should be able to fill everything in. So the mass of the ball is 2.5 grams. Gravity is 9.8. We're doing this experiment on Earth. Epsilon will be voltage over 0.12 meters, and then times the charge, which is 9.6 times 10 to the minus 6. The only number I don't know there is voltage. So you go 0.0025 is 2.5 grams times 9.8. So that's my left side. So divide by 0.12, so I take it over there, becomes multiply by 0.12. Multiply that becomes divide by that. And we get a voltage of 306. Okay, that's A. And B is right there. It says which one's positive, top or bottom. Okay, question 8. Draw a field around a single positive sphere. Okay, positive sphere, and it says, now you got to ask yourself, if I drop a positive test charge right here, where's it going to go? Well, it's going to repel. Right here, it's going to repel. Right here, it's going to repel. Okay, so a positive test charge will repel in all different directions. Direct it away from that. Number 9. It says draw the field around two positive spheres sitting side by side. Okay, so yeah, over here that's no problem. Drop a positive charge, takes off. Positive takes off. Out here, yeah, I can see that taking off in that direction too because it'd have two forces pushing it away. Inside here though, if I put one right there, it's going to get pushed away from this one, but that guy's going to push on up too and it's going to curl outwards. These guys are going to curl outwards. Same with here. A bit like that. Okay, so that's all I have to do. If I put one right in the middle, you can get it to float there maybe, but you're basically saying what would happen if I dropped a positive charge there. It's going to shoot out that way. Okay, in between you get some different dynamics there. Okay, number 10. So we're going to squeeze that guy in here. A wire is placed in a horseshoe magnet with north being at the bottom. So let's see if we can kind of draw this in 3D then. North at the bottom, south at the top. Kind of looks a bit like that. It's kind of skinny at the top. Okay. So the wire's going to go through here. North and the bottom. So my fields are going to be going up because magnetic compass needles point to the south pole of a magnet. The electron current is flowing north. Okay, so there's this wire here. This is sitting on the ground in 3D. That's north. So we'd have west, east, south like this. So west is into the magnet, east is out of the magnet. In which direction would the force be? The electron. It says electron current. So the electron current is going in, is flowing north, along that way. So it's electrons, so we use our left hand. What direction would the force be in? So my fingers need to point towards the south. My thumb has to point that way. I'm going to be pushing that wire inside. Inside would be west. So that's going to head to the west. So 9. This was 10. Number 10 is to the west. Okay, let's jump up to question 11. 11 says the wire in the last question has a current in it. The magnetic field strength. Okay, so that's still in view. So number 11, the force will equal the current times the length of the wire times the field strength, and then times sine if it's not coming in straight, but it says it's fine. So what would the force be? So let's see what the current is. 1.6 amps. Length of the wire is 20 centimeters or 0.2 meters, and the field strength is 0.23 Teslas. So we got 1.6 times 0.2 times 0.23, and I get really small force, 0.0736 newtons. Okay, not much force, it's only 20 centimeters of wire. Okay, let's take a look at number 12. A proton enters a magnetic field. Okay, here we go. From the west. So, okay, the proton is going this way. It's going east. The magnetic field and is directed down. Okay, so we can show that like this here. The magnetic field's going into the pages, so these will be X's. These aren't wires, this is the field. It's basically saying if I had all these compass needles, it'd be pointing into the page. Okay, so the proton enters the magnetic field from the west. At that speed, the magnetic field is at and directed down. Find the magnitude and the direction of the force on the electron. Oh, it must be a typo. Should be a proton here. So the proton comes in, I'm going to use my right hand. So now my thumb is the direction of the proton, and my fingers have to point into the page, and my thumb's this way, so I'm going to be pushing that guy up. He's going to make a turn like that. He's going to head to the north. Okay, so he's going to head north, but let's find out what the force is on that guy. Force equals the charge times the velocity times the field strength. And then a sine factor if it's not coming in straight. So the charge, it's a proton, 1.6 times 10 to the minus 19. The velocity, 6.4 times 10 to the 6. And the field strength is 2.4 Teslas. Let's find the force then. So 1.6 exponent 19, 6.4 exponent 6 times 2.4. We got a small number. 2.46 times 10 to the minus 12 newtons. And the direction we said was north. Okay, because you have to use your right hand. Fingers are pointing in, but my thumb has to point in the direction. So that's going to push it up the page, and that's north, south, west, east. And it was coming from the west. Okay, 13. The proton in the previous question travels in a circular path while in the magnetic field. Determine the radius of the path. Okay, 13. So if we solve the equation that centripetal force equals mv squared over r, and my force will be qvb, okay, we can cancel out one of the v's. If I'm solving for r, R equals mv over qb. 99% of you guys are probably just going to memorize that formula, which is fine, saves you some time. Mass of a proton, velocity was 6.4 times 10 to the 6. The charge was 1.6 times 10 to the minus 19, and the field strength of that field was, the magnetic field was 2.4. So I got 1.67 6.4 exponent 6 times, and we divide by 1.6 exponent 19, change sign, divide, and then I divide by 2.4, and that comes out to 0.0278 meters, okay, which would be the same as 2.8 centimeters. Okay, one more question to go. Question 14. Draw a magnetic field where the field is directed out of the page. Draw the complete circular path a positive charged particle like an alpha particle would take. Okay, so magnetic field out of the page. That means all the compass needles are pointing up towards you. Okay, so that would be like having the magnet with the north on the bottom and the south on the top. It's going to make a circular path. I have a, okay, so let's draw a circle here. Circle like that, and it's traveling in a circle, so the force would always have to be directed center-wise. So let's see what we got here. Positive particle. Positive particle, you have to use your right hand. The field lines are coming up, so it's going to be kind of tricky. So my fingers have to point up, and my thumb has to point this way then. Okay, which means this guy's traveling in a circle this direction. He's going around and around that way. And as my hand turns, the palm of my hand is always pushing towards the center of the circle. Okay, so it's a clockwise direction.